Hello. Today we're going to talk about color-based vehicle tracking in a video using Kalman filter, which implements a fractional feedback mechanism. So what we have essentially planned to do is that we intend to track a single object, a single car, most preferably, uh, based on its color. So you know what we're going to do is we're going to let the user define the color of the car he wants to track, and we'll implement it using our C++ coding techniques over a OpenCV platform to get the required results. What Kalman filter does is that it uses information from previous iterations, as in errors in measurement or errors in data or measured values, previous measured values, and it tries to uh, estimate what my next measurement could be. When I have uncertainty about what my next measurement could be, we're going to use a Kalman filter to predict what it might be. So the most important thing is the Kalman gain. We'll get to it, but let me give you a rough idea about it. Kalman gain is sort of like a ratio that you know helps converge from the predicted value at a faster rate towards the measured value, and which is the actual value. All right, so let's get into the methodology used in calculating the Kalman gain and henceforth carrying out the procedure for prediction using Kalman filter. Now, Kalman filter can be broadly divided into three different stages. Now, stage one is where Kalman gain is calculated, stage two, where current estimate is calculated, and stage three for calculating new error in estimate. Now, basically, Kalman filter works with four different parameters, three of which are constants. Now, these three constants are original error estimate, error in data, and the original estimate. And the lone variable is measured value, which is provided by the sensors or inputs that are given by different devices. Now, coming to stage one. Stage one comprises of calculating the Kalman gain. Now, what Kalman gain does is that it is sort of like a value that gives weight to the difference between the estimated value and the measured value. So if my difference is very large, it means that my system is not functioning very well. So there has to be major changes in my algorithm updates. So the Kalman gain value tends to be a very large value towards 1, which is the maximum value. So when my Kalman gain is large, it means that major changes are required in updates and that my system is not performing well. Now, Kalman gain is defined as error in estimate to the sum of error in estimate and the measured value, right? So what Kalman gain is doing is it's sort of like saying, you know what, your methodology is not exactly perfect, so I'm going to give you a chunk of difference that is obtained that you need to use to ensure that the convergence occurs at a faster rate. Now coming to stage two is where current estimate is calculated. What stage 2 does is it works with three different parameters: the Kalman gain, which was calculated in stage 1, the previous estimate, and the measured value. So what stage 2 does is it uses all these information and tries to estimate what my next uh, position could be, right? So that's what the stage 2 does. What stage 3 does is it's more related to providing updates for my next iteration. Now this update is more in the form of errors that will be needed to update for my uh, next iteration. So this is what the Kalman filter can broadly function at, you know. So I've got three stages: stage 1, stage 2, stage 3. Now all these iterations keep happening again and again and again, and the corrections keep happening again and again. So the Kalman filter is such a recursive process, and that's exactly what makes it so efficient. Because Kalman gain is so iterative that the convergence is way faster than the other possible mechanisms that could be used. Now that's the specialty of Kalman filter.
Kalman filter mainly have two matrices, namely process covariance matrix and state matrix. State matrix usually deals with the velocity and position. Now we want to predict the new state and process covariance matrix. New state matrix can be predicted using the previous state matrix and control variable matrix along with adaptive matrices which are used to get the desired form. There is some amount of noise also present during these calculations, and to get the new predicted covariance matrix we will use the previous covariance matrix plus some noise. Now after obtaining this we want to find the Kalman gain. Kalman gain can be obtained using the predicted process covariance matrix and some H variable matrices. And after obtaining the Kalman gain we will also obtain the values of the now what you say called measurement input, and measurement input is obtained using the measurement state matrix along with noise. After obtaining these values we will now calculate the new state. That means we're updating the state based on the predicted and measured input. So we will get now the updated matrices, along with we'll also find the updated process covariance matrix. And updated process covariance matrix and state matrix uses the Kalman gain as parameter. After that we will update the output of the matrices. That means we will get the output of updated state xk and pk converted to the previous state in the next process.
Okay, let's get to the algorithm part of my coding techniques that will be used. Now, we start our algorithm with a start block, which is common, and then we get to the import OpenCV modules where we need to import all the required libraries, modules to help our functioning, you know, in a more smooth fashion. And then the third block is where the user interference steps in. The user is given a choice to select a small range of colors that he or she might need to track the desired curve. Why the range? It goes like this. Just because a red car is filmed using a camera, it does not necessarily mean that the video that I'm going to take will, will have a car that is purely red. Due to many factors, there may be a few changes in shades of red. So we let the user decide what range of colors he or she would like. And then next we get to initializing the matrices required for Kalman filter. And then we read the file, and in our case, our file is the video that has been broken down into frames. Now then we smoothen out the noise. Now this is the first step because smoothing of noise has to be the prerequisite before getting to HSV conversion and color thresholding, because if noise is not taken out, there's a very high chance that the noise itself will be used for HSV conversion or color thresholding, which will yield an absolutely disastrous results. So first we smoothen out the noise. Then we get to the HSV conversion. Now HSV stands for hue saturation value. What it means is this. As I explained before that red can have a few shades of red, it pertains to the hue values of red, you know. So we've got a basic red, a little more towards the orangish side, a little more towards the darker red maroon sides. So that is what we do. We using our HSV conversion techniques to convert that band of red uh, objects in our frame to something which is more white, which can be used to detect, and the rest of the background is changed to black because we do not need to track that. We may detect it, but we do not have to track it. Now let's get to the color thresholding. Color thresholding is where we use techniques to segregate objects based on its color. Now, well, how is it different from HSV conversion? HSV is more like a band of allowed uh, colors that need to be detected. But color thresholding is where you fix on to even narrower band and we lock on to the target, right? And now morphological processing is our next block. So morphological processing is solely used for edge detection and motion detection. Well, morphological processing also consists of dilation and erosion on multiple levels, but the output of morphological processing will always be about edge detection and motion detection. Now, morphological processing is done to detect the edges. Cool. Now, what next? What we do is we have to threshold that. And by thresholding, I mean we want our tracked object to be the only thing that is being tracked, even though there may be different color particles or objects in my frame. I do not want to track that because we're locking on to a car. Let me give you an example. Let's go to the red car again. Let's say a red car is going over a road and there's something red on the side of the road. I do not want my mechanism to sticking onto the red object to the side of the road and leave out my red car, which will be disastrous. So we want our mechanism to stick to the moving object. So that is where thresholding viewing comes in. And this, in combination with HSV conversion, color thresholding, and morphological processing, sticks on to the car that is being tracked and stops detecting the rest of the objects around the car. Now let's get to contour detection. Now contour detection, as simple as it may sound, is the most important thing because it is what defines our entire process of tracking. We talked about how tracking is done by locking onto a car and thresholding viewing, but in contour detection what we do is we find the centroid of the moving objects and we draw a bounding box around it, and as the object moves our bounding box also moves, thereby sticking on to that tracked position. Now, all this is may sound a little, controversial with each other, but smoothing of noise, HSV conversion, color thresholding, morphological processing, thresholding, viewing, contour detection, all these 6 stages work together as a single unit to allow the tracking mechanism to function smoothly, and this is the heart of the entire process. Now, let's get to the penultimate block, prediction using Kalman filter. Uh, and in this block, we define feedback mechanism. What feedback mechanism does and what it translates into when it comes to coding techniques is this. Fractional feedback mechanism plans at taking a mean of all the gains of previous iterations to stabilize the movement, and we add the new gain we have obtained to the previous mean that has been just recently calculated. So what it does is it takes the mean of all the previous iterations, adds it to the mean of what our present calculated mean is to provide a stable outcome. Now that's what fractional feedback is. Now we use prediction by Kalman filter to detect where my next position of my car could be. And then the final stage is Kalman update. So we update all our variables, parameters, matrices so that we can get to the next iteration, and in our case, which is a frame, to predict and detect the subsequent frames and car images in my subsequent frames.
graph which you are seeing corresponds to the helicopter car chase video which you've seen earlier. Now this graph shows the x coordinates of the pixel location of the centroid of the boundary boxes. So here the green plot which you are currently seeing corresponds to the centroid of the boundary box of the detected boundary box. The blue plot which you are seeing here corresponds to the centroid of the boundary box which uses the basic Kalman filter to predict. The red graph is corresponds to the centroid of the boundary box of the proposed algorithm which implements a fractional feedback on the Kalman filter. Here you can see the green plot goes to 0 in at some places. That indicates that the car, as it goes behind the trees, it becomes invisible. That's why we've made the graph go to 0. When the car is invisible to the camera, the Kalman filter still predict it. That's why they have a graph, I mean they have values existing for that. Now as you can see here, the two plots corresponding to the basic Kalman and the proposed Kalman filter have very less deviation. What I'm trying to say here is both track the car, but the proposed algorithm tracks it much effectively and much accurately than compared to the basic Kalman. At the sudden disappearances or sudden appearances of the car, as you can see, the basic Kalman undergoes sudden fluctuations, but that doesn't happen with the proposed algorithm because due to a fractional feedback, it gets stabilized. This graph corresponds to the second video which was showed earlier, in which a toy car was moved. This video has been shot from our phone camera. This graph also is also similar to the previous graph which you've seen. The green plot corresponds to the detected boundary box. The red plot corresponds to the boundary box which uses the proposed Kalman algorithm, and the blue plot corresponds to the basic Kalman algorithm. Uh, when the toy car goes behind the green plate, it becomes invisible to the camera. So that's the reason that green plot goes to 0 for some amount of time, during which the basic Kalman and the proposed Kalman filters predict the location of the car. As you can see here, the proposed and the basic Kalman have tracked it, but the proposed algorithm was much accurate and it's more stabilized than compared to the basic Kalman. You can see at the edges where it's suddenly going invisible and visible, the basic Kalman tends to sudden fluctuate, but the proposed algorithm is more stable because of the fractional feedback which stabilizes the gain.